Let's start the final step of our analysis, which is about the post-processing of our results, or the interpretation of effect of different parameters on the instability condition. This expression is the solution of the dispersion relation, or the roots of the quadratic dispersion relation which was obtained in the previous step. You know, any quadratic equation has two solutions. This is the delta of that quadratic equation. We have the square root here. Based on my explanations in step 5 about normal modes, the important point here is that the value of the frequency, or sigma, should be complex. Sigma should be a complex valued number. And alpha is a real valued function. So, this is the sense of temporal instability analysis. So, alpha here is a real valued number. So, and densities and also velocities are all real numbers. So, this expression is a real number. The only origin of production of an imaginary part in this relation is the term under the square root. So if you want to have a complex valued sigma for frequency, the term in the square root should be a negative number. So it's easy to compute the value, the condition that this expression is negative. So you have the difference of the velocities of two streams squared is greater than a combination of the wave number of the disturbance appearing on the interface and the gravity acceleration, the difference of densities, and also the surface tension coefficient. I've ignored the effect of surface tension in my derivation of the relation in my lecture. It's a good exercise for you to include the surface tension in the dynamic boundary condition. This is the new form of dynamic boundary condition, including the surface tension. Kappa is the curvature of the interface. So if the curvature is 0, it means that the pressure of 2 points on the interface are equal, which is our condition in this lecture. Okay, so use this new version of the dynamic boundary condition and rewrite all equations and obtain the new determinant of the matrix of coefficients and for homogeneous system of equations, and again obtain a new form of the dispersion relation, and the roots of that new form includes the surface tension coefficient here. Okay, this is the instability condition, or the case with growling disturbances on the interface. There are some important extra remarks about this relation. You have to compute the minimum value of this expression, or the extremum of this expression, which is a minimum extremum point, because this term is greater than this one, and this expression is greater than a question mark. So here I have to compute the value of this question mark. So you know how to compute the minimum of a function with respect to alpha. Alpha is the wave number of different disturbances appearing on the interface. So take the derivative of the circle. Circle here is this expression with respect to alpha equals 0. This yields the minimum alpha. It means the wave number for which the magnitude of this expression is minimum equals square root of gravity acceleration times the difference of densities over surface tension. Also, in temporal instability analysis, as I mentioned in step 5, alpha is a real number. So we have another square root sign here, so the expression in the square root should be a positive number. the value of the gravity, acceleration, and the surface tension coefficients are positive always, but the magnitude of the density difference may become negative. To have a real alpha, the density of fluid 1, which is underneath the interface, should be greater than the density of the other fluid. This is the point I mentioned at step 1 in the introduction. In pure Kelvin-Helmholtz instability, the density of the lower fluid under the interface should be greater than the other fluid because of the gravity effect. The other interesting case is when the densities are identical. It means two fluids are similar and only the velocities are different. And the final point is about the water waves. Water waves are some kind of waves which are created on the free surface of water in lakes and oceans. You can simplify this condition by assuming the density of the water, which is a liquid, to be greater than the density of the air above the water, which is a gas. So in this relation, you can ignore this term in comparison to the other one, and again, rho 2 in comparison to rho sub 1. And also, rho sub 1 cancels from the numerator and the denominator of this fraction. And suppose that the velocity of the water is nearly zero because the density of water is very high and higher than the density of air, and the inertia of the air cannot change the velocity of the water. So u sub 2 here is again 0, and this equation is the simplified form of this instability condition, which is for water waves or the blowing winds over the free surface of water.